ELO ratings are a ubiquitous way to compare players in any two-player game or sport. It was initially proposed by Arpad Elo for an objective way to rank chess players, and has since been adopted by a wide variety of games and sports like Go, Scrabble, tennis, and even high school debate. Each player has an ELO rating that goes up whenever they win a game and down whenever they lose a game. But the amount your rating goes up or down is not constant. If it was, then highly rated players would just face off against noobs all day to farm a lot of points. The ELO system posits that if you beat someone with a much lower rating than yourself, you should only earn a small amount of ELO. And then when you occasionally lose to a much lower rated player, you lose a sizable chunk of ELO. On the opposite side of the ledger, players are rewarded with a lot of ELO for beating much higher rated opponents, and aren't penalized very much for losing to much higher rated opponents. Because of these dynamics, it's hard to game the ELO system. The only reasonable way to increase your rating is to beat other good players. Nevertheless, there have been rumors and accusations of collusion among players to boost particular players' ratings. On the screen are some examples from chess. This leads to a natural question. If a group of people, none of whom are any good at chess, conspire to play a total of k games against each other with predetermined outcomes, just how high could they get one of their ratings to be? There are two mathematical ideas I hope to communicate through this video. The first is the utility of conversion between discrete and continuous processes, and the second is the concept of a potential function or mathematical invariant. Let me describe more precisely how ELO works. Each ELO system specifies a pot function, which we denote sigma. And after a game is played, sigma of the loser's rating minus the winner's rating is added to the winner's rating and subtracted from the loser's rating. Let's plot an example of one such sigma. Here we have the sigma used by FIDE, the International Chess Organization. It's a scaled version of the logistic growth function. To see that this setup matches what we described earlier, notice that if the winner's rating is much higher, they will only gain a small amount of ELO. And conversely, if their winner's rating is much lower, then they earn a large amount of ELO. This is not the only value of sigma which has this property. Actually, Arpad Elo's initial suggestion for a sigma function is the cumulative density function for a Gaussian distribution. There's a whole video one would be able to make about the theory behind why you would prefer one version of sigma versus another. But for our purposes, we're going to abstract away from this and just consider a generic pot function sigma that satisfies only a couple basic properties. The first is that it's monotonically increasing. That's the whole purpose behind ELO.
The second two properties are that sigma is positive and bounded. This ensures that you always win something for each victory, and that there's a cap on the most number of ELO points you can get from a single win.
The last remark I'll make is that in the case of a draw, you just average what would have happened if you won and if you lost the game. As a warm-up, let's think about what happens when there are only two schemers. Let's name them Winston and Lucy. We can track their ratings on this plot, where the x-axis denotes Winston's rating and the y-axis Lucy's rating. For this example, I'm just going to use the normal sigmoid function as the value of sigma. Depending on the outcome of a game between Winston and Lucy, the point representing the pair of their ratings moves either up and to the left or down and to the right. So here in this diagram, if they both start with 0 rating points, the red arrow corresponds to a win for Lucy, and the green arrow a win for Winston. Imagine if initially Winston had 1 rating point and Lucy was at 0 rating points. Then you can see a win for Lucy rewards a lot more ELO points than a win for Winston. Conversely, if Winston started 1 point behind Lucy, then a win for Lucy does not garner as many ELO points as a win for Winston. Let's see what happens when these two players play a sequence of games against each other. Maybe initially they alternate which one of them wins the game. Or maybe Winston wins many games in a row and only occasionally loses to Lucy. From this picture, however, it's clear that all of this back and forth is not helping one of them boost their rating really high. In order to boost one of their ratings really high, they should just have them win over and over again, like this. So the question now becomes the following. If Winston wins K games in a row against Lucy, how high will he be rated after those games? There's actually two ways I want to think about the solution to this problem. The first is more analytic, and the second is more geometric. Let's start with the analytic way. Note that Winston's rating after T games have been played can be represented using this recursive formula. His rating at time t plus 1 is his rating at time t plus the amount of elo he garners on the tth game. This amount is sigma of Lucy's rating minus Winston's rating. But Lucy's rating is always equal to minus Winston's rating because the sum of their ratings is constant. This means the amount is just sigma of minus 2 times Winston's rating. We can write this formula in a little bit more of a compact way as this. The change in Winston's rating is equal to sigma of minus 2 times Winston's current rating. Now here's where we convert things to a continuous process. Instead of this delta being a discrete change from time t to time t plus 1, we can replace it with the derivative with respect to t. That is, the continuous change in r with respect to time. If you've ever taken a differential equations class, you might recognize that the initial discrete update equation we wrote down is actually the Euler's method approximation to this continuous differential equation with a step size of 1. For this particular differential equation, it turns out that Euler's method provides a good approximation of the solution. Therefore, if we solve the continuous differential equation, we will have a good approximation of what Winston's rating actually would be after K games are played. Now we can analytically start to solve this differential equation just using separate and integrate. And that gives us this integral equation. Without a particular value of sigma, this is sort of as far as we can go. Each value of sigma will give a different value of this integral. But here we just have an abstract sigma, so we can't explicitly compute what this integral is. Now, before going further, I want to describe the second perspective on the solution. Let's look back to this diagram. The number of games played is the number of line segments making up this continuous path from 0, 0 out to RR. Rather than counting line segments, I think it's a little easier to think about counting endpoints to line segments. Let's think about how many endpoints there are in a small window near the point x, y. Well, the distance between consecutive endpoints, as measured in their x or y direction, is just sigma of y minus x. And therefore, the density of dots near the point x, y should be just the reciprocal, 1 over sigma y minus x. Now, of course, we already noted that Lucy's rating is always just the opposite of Winston's rating, i.e., we are always on the line y equals negative x. So this expression for density simplifies to just 1 over sigma of minus 2x. And wouldn't you know it, that's exactly the integrand. That's exactly the quantity we would need to integrate from 0 out to r in order to estimate the number of dots on the interval. Let me introduce a special function f, which represents the antiderivative of the reciprocal of sigma. It is in terms of this function f that we can represent Winston's rating after K games. For the particular sigma of the normal logistic function, f is this exponential function. So f you should think about as a really quickly growing function. And you can see that the solution to Winston's rating after k games is proportional to the inverse of this f applied to k. So for this logistic function, that would mean that Winston's rating grows as the logarithm of the number of games played. In this table, you can see what Winston's rating after k games would be if various pot functions were used. Like I mentioned on the previous slide, for the sigmoid function, which is what FIDE uses, it grows proportional to the logarithm of the number of games played. If they used Arpad-Ilo's initial suggestion, it would be even slower at only the square root of the logarithm of the number of games played. The conclusion here is that if only two players are scheming in this way, they're unlikely to make it very far. Let's analyze things at the other extreme, where n is so large it's practically infinity. That is, the group of players is only constrained by the total number of games they play, and they have as many people in on the scheme as they need. Let's review the lesson from the two-player case. Once Winston's rating became higher than Lucy's, he could no longer gain much elo from her. It's therefore only worthwhile for a player to beat others who are close to their own rating. Let's take this idea to its extreme and see what happens when two players only face off if they have an equal rating to each other. Because the difference between the winner's rating and the loser's rating will always be 0, this means that everyone's rating increases in increments of sigma 0. In this demonstration, I'm going to loop through the foxes from left to right and find the first pair of foxes with equal rating and have the left fox beat the right fox. For n equals 8, after just k equals 30 games have been played, the foxes have sorted themselves into this order, where each fox has a different multiple of sigma 0 as their rating. Let's see another demonstration of this dynamic. This time, I'm going to pick a random pair of foxes with equal ratings to face off each time. Remarkably, the same thing happens. After 30 games, the foxes have sorted themselves, with the highest rated fox being rated n over 2 times sigma 0, and the lowest rated fox being minus n over 2 times sigma 0. What these examples demonstrate is that after enough games have been played that the foxes all have distinct ratings, one of them will be rated n over 2 times sigma 0. What we still need is a way to track the player's ratings before we get to this final state. To do that, I'm going to introduce a potential function. In this case, our potential function is going to be the sum of the squares of all of the fox's ratings. Let's see that demo again, but this time I'm going to be tracking the value of the sums of the squares of all of their ratings alongside the number of games that have been played. Did you notice a pattern? It looks like the sum of squares is always just twice k times sigma 0 squared. Let's see if we can prove this conjecture. When one player increases their rating by sigma 0, and another player decreases their rating by sigma 0, see what happens to the sum of the squares of their ratings. The expression simplifies, and we see that the sum of the squares of their ratings increased by exactly 2 times sigma 0 squared. And because the sum of the squares is initially 0, this proves the conjecture. It turns out that this simple observation is enough to get our main result. Let's let R represent the highest absolute rating after k games have been played. As we saw, when k is large enough, R will be n over 2 times sigma 0. On the other hand, if k isn't large enough so that the foxes have all separated, then the sum of squares is just 2k times sigma 0 squared. And of course, the sum of everyone's ratings squared is going to be at most n times the largest rating squared. And this inequality can be rearranged to be a lower bound on R. So notice that we have two lower bounds on R. And in all circumstances, one or the other of these two lower bounds is going to hold. So in general, the minimum of these two bounds always holds. If you're given a budget of k games you're allowed to play, a balancing argument shows that n equals 2 times the cube root of k is the optimal number of players to recruit to your scheme. Using this value of n, we see that this strategy of only having two players face off against each other if they have equal ratings will allow one of them to achieve a rating of at least the cube root of k times sigma 0 rating points. You might now wonder if some strategy does better than this one. The rest of this video will be dedicated to showing that, while it might be possible to do a little bit better, there's a limit to how much better any strategy can do. Let's make a plot of the number of games that are played k versus the highest possible rating someone might have after those games. What we showed in the previous section is that there is a strategy which achieves or surpasses this line of r equals the cube root of k times sigma 0. It turns out that this sum of squares potential also allows us to derive an upper bound on r in terms of k. Certainly, just the highest absolute rating squared is less than the sum of everyone's rating squared. And this, in turn, turns out to be less than k times some constant which depends on sigma 0. When players only played against each other with equal ratings, then instead of an inequality here, we had an equality. And instead of this c sub sigma constant, we had just 2 times sigma 0 squared. However, in general, when any two players can play against each other, we only have an inequality with this slightly larger constant c sigma. Rearranging this inequality immediately gives us an upper bound on r in terms of k. Namely, r is upper bounded by the square root of k times a constant. This allows us to conclude that the highest possible rating one could achieve after playing a total of k games is somewhere in between a value proportional to the cube root of k and the square root of k. Now, this is still a pretty sizable gap. In order to close the gap between these upper and lower bounds, we would either need to come up with a better strategy which achieves a rating higher than the cube root of k after k games, or come up with a different proof technique which shows a stronger upper bound on r than the square root of k. We're going to take the second approach. In order to do this, it'll be a little bit more convenient to think about these upper and lower bounds in sort of the opposite form, where if I want to achieve a total rating of r, the number of games I must play to reach there is somewhere in between r squared and r cubed. So our current upper bound comes from this inequality, that r squared is less than the sum of squares, which is less than some constant times the number of games played. Now, we would really like to improve this r squared to an r cubed, perhaps using a different potential function that is also bounded by some multiple of the number of games played. What gave the sum of squares this property? Well, we showed that the change in the sum of squares after each game is played is upper bounded by some constant value. It turns out we already saw the definition of another function which also changes by at most a constant value every time a game is played. Let's recall the definition of f. It's the antiderivative of the flipped reciprocal of sigma. We can model how the value of f of x changes as its input changes by thinking about the first-order Taylor series approximation of f. The expression for this Taylor series can be simplified a little bit using the definition of f with the fundamental theorem of calculus. If we let x represent the difference in two players' ratings, let's say Winston and Lucy's, and delta represent how that difference in ratings changes when Winston beats Lucy, then the change in f of x is going to be roughly 2, according to this Taylor series approximation. Let's combine the sum of squares idea with this new f idea to design our new potential function. Let r sub I be the rating of the ith ranked player. So r sub 1 is the highest rated player. Let's let the potential equal the sum of squares of all the ratings plus f of the difference between consecutive players' ratings. We can see this potential function in action on the diagram on the right. The height of each fox on the screen corresponds to their rating. There's a total of 4 foxes, and so the potential function includes 3 terms involving f.
Watch what happens when the ranked number 2 player beats the ranked number 3 player.
The first term decreases because the number 1 and number 2 players came closer together in rating. Similarly for the third term. For the second term, notice that the number 2 and number 3 players became further apart in rating, so that term is increasing. However, the analysis using the Taylor series on the previous slide is what allows us to conclude that this increase is not too much. Watch instead what happens when there's an upset. Say, for example, the player number 3 beats the player number 2. Because this is an upset, the third-ranked player earns quite a bit of elo, and the second-ranked player loses quite a bit. This causes the difference between the first and second player's ratings and the third and fourth player ratings to increase by a substantial amount, and therefore the first and third terms involving f increase by a lot. So we're only able to argue that the change in potential is upper bounded by a constant when a non-upset is played. In other words, the potential is only upper bounded by some constant times k, the number of games played, as long as none of those games are upsets. The second step of this strategy is lower bounding the potential function in terms of r. Previously, we had the lower bound of r squared, but we really wanted a lower bound of r cubed. Let's see what this rating function gets us. We can use this intermediate variable, which is the number of players who have at least half as many rating points as the highest rated player. This allows us to derive a lower bound of the potential both in terms of the highest rated player, R1, and m. Taking the worst case value of m results in this lower bound of potential in terms of just r. Remember that when sigma is a sigmoid used by FIDE, then f is an exponentially growing function, so f inverse is logarithmic. Let's put a pin in this assumption that there aren't any upsets. This gives us the main result. We previously showed that if you want to achieve a rating of r, you don't need to play more than r cubed number of games. On the other hand, this analysis shows that at least r cubed divided by f inverse of r squared are necessary. And remember, when sigma is the logistic growth curve, for example, the one used by FIDE, f inverse grows really slowly, like logarithmically. So this shows that the number of games one must play to achieve a rating of r is somewhere in between r cubed and r cubed over log r. Let's return to this assumption that no upsets occur. Let's look at a diagram involving just 3 players. Here I have a projection of 3D space where each axis indicates the rating of either Winston, Tyrone, or Lucy. Here we're going to think about Winston being higher rated than Tyrone, who's higher rated than Lucy. We can now think about which direction we move in when different games occur among these players. If Winston beats Tyrone, we move in the direction of this green arrow. Conversely, if Tyrone beats Winston, we move in exactly the opposite direction. Notice that these arrows are perpendicular to the axis representing Lucy, whose rating does not change when Winston and Tyrone play. We can similarly draw arrows for when Tyrone beats Lucy or Lucy beats Tyrone, and finally for when Winston beats Lucy or Lucy beats Winston. I've color-coded all of these arrows, so Winston, Tyrone, and Lucy each have a primary color, and the arrow corresponding to a game between them is colored with the mixture between their colors. We can move the starting point around a little bit to get a sense of how far in each direction one game would move us. Let's zoom way out on this diagram and see what happens when Winston beats Lucy once, and then these 3 players alternate between Winston beating Tyrone and Tyrone beating Lucy. Let's see what happens when some upsets occur. Maybe Tyrone beats Winston, and then Lucy beats both Winston and Tyrone in turn. According to the diagram, it seems clear that these upsets are just counterproductive.
This is definitely true for upsets that occur at the end of the sequence of games, because they can only decrease Winston's rating. However, for upsets that occur in the middle of the sequence, One might speculate that these upsets allow one to maneuver in a clever way around state space that allows Winston to go on to more easily earn ELO points.
This is where that conversion between discrete and continuous processes comes in handy. Rather than think about a sequence of games, we can think about one path made up of many line segments, each line segment of which corresponds to one game. And rather than count how many line segments there are, we can integrate the density along the path for a good approximation. The density while traveling along each of the solid colored directions is listed here. Take a moment to think about why this matches the idea of density introduced when we had just 2 players. The final piece of the puzzle comes when considering an upset followed by a non-upset. There are 6 possible ways that can occur among the 3 players. They correspond to these 6 diagrams in state space. Each of these corresponds to 2 line segments that make up part of the original path, one corresponding to an upset, followed by one corresponding to a non-upset. In each of these 6 cases, we can perform an edit to the original path so that the second line segment corresponds to an upset. In other words, the upsets are pushed further to the end of the path. In each of these 6 cases, the resulting path after the edit is either just as efficient or more efficient than the original path. To see the role this plays in the eventual proof, let's suppose someone hands you a path through state space that they claim represents a very efficient way for Winston to become very highly rated. Using those update rules, we can keep the endpoint of this path the same while making edits to the middle that make it more and more efficient. And once no more replacements can be made, this means that all the upsets occur at the end of the path. But our goal is to get Winston to be as highly rated as possible, so these ending upsets do nothing to benefit us, so we can simply remove them. The conclusion is that the most efficient way to boost someone's rating is for no upsets to occur among the colluding players. We are therefore justified in the final conclusion, when sigma is a logistic growth function, that the number of games one must play in order to achieve a rating of R is asymptotically between R cubed and R cubed divided by log R.
That's all for this video. Thanks for watching. If you want to see any of the details that I glossed over, be sure to check out the full paper linked in the YouTube description.